Thank you, Andreas, for the kind introduction, and welcome everybody here to my presentation.
Today I would like to talk to you about how we use the nLIGHT's AFX1000 laser.
I'm very happy to be here today and be able to present our results on the spatter formation, especially the spatter formation and dependency of a beam shape.
Thank you. It's a pleasure to be here today. I'm here to talk endlessly about metal additive manufacturing.
I would like to talk to you about the project we did together with nLIGHT.
Yeah, thank you very much for the kind introduction.
Good morning, everyone. So I'm very happy to be here to show some latest results. We worked together with nLIGHT for the remote laser study.
I will give a presentation about our experience with beam shaping.
Thanks for having me again, and I'm glad to show you our latest results on processing with the AFX laser.
Thank you, Andreas, for the kind introduction.
I like the video on the left-hand side a lot. It shows the typical powder bed fusion, so additive manufacturing processing, where you see a highly dynamic process. So in the middle, the bright spot is the actual laser beams. You see a highly dynamic process, and actually the process is not that fast, right? It looks quite slow, and you have this typical hedge-wise exposure, and typically you use Gaussian beam profiles. And what you can also see is quite nicely the spatter formation. Spatter formation is something which is always not that good, because the spatter formation may lead afterwards to defects in the process. So state of the art are Gaussian beam profiles, high laser powers, of course, and more or less low scan speeds, and this may lead to effects like overheating, spatter, or balling, which you can see in the video.
And if we're sending a lot of power in, we're generating condensate. We're not selectively laser melting. We are selectively laser boiling. We are boiling the metal, generating lots of vapor. It consolidates in the chamber in the form of very fine particles, submicron particles, pyrophoric particles. They are jumping around in the atmosphere. They're causing laser obscuration by getting in the way of the laser beam, which results in defects on the melt bed. And then we're also creating a lot of ejection of molten material, weld spatter. And as that jumps out of the melt pool, it coalesces into a very large ball with a gas pore in the middle, drops back down on the bed, and we might weld it in, we might not weld it in. It's kind of big, and it's going to have a void in the middle of it. So this all generates a lot of defects.
So for typical Gaussian beam profile, you can see, well, when you increase the power, since you have very high peak density at the center, so the keyhole mode was starting to generate very fastly.
It matters how the energy is distributed into the material. Shown at the bottom right of the graph is, if we simplify the Gaussian profile, we have in the middle of the profile a high intensity peak, which might lead to evaporation of material, and so the chemistry, the alloy changes, and it's not what we want to produce. On the same time, at the edges of the Gaussian beam profile, the energy is not high enough. So, quote unquote, we lose some energy because the energy is not high enough to melt the material. So there is the idea, if we can distribute the energy more clever, like a ring shape, for example, or other possibilities, we might couple more energy into the material and increase, therefore, the productivity.
The biggest challenge is that within this printer, it is an assembly of a lot of complex subsystems that move powder, convey powder, spread powder, heat the platen, move the platen. There's process gas flow, there's process gas filtration, there's the energy source, there's the scanning. All these subsystems have to work together, and they all have to be equally good. Now, we're working with this amazing laser, AFX1000, 1,000-watt multi-mode laser. It is an amazing tool to work with, but what we're going to find also is that if all the rest of the subsystems aren't as good, it gives us a lot of challenges. And this is what's been at the root of this slow advancement in laser powder bed fusion.
And decrease the spatter formation. And this is actually done in our case with different kind of ring-shaped beam profiles.
I guess everybody knows that LPBF is in general a very complex process with interactions of various physical phenomena like absorption, heat conduction, or evaporation, which is not fully understood right now. But as a machine manufacturer on the one hand and operator on the other hand, it's our passion to ever better understand this process and to influence this chaos in our favor. And one way to influence this is the heat source, for example, with the AFX beam shaping laser, with 7 different intensity distributions. Besides the Gaussian one, the common Gaussian one, the operator can use the ring beam and 5 more intensity distributions in between, differing in the ratio of power between center and core. And so the operator is enabled to not just only print filigree parts with high precision, but also mixed geometries and optimized parts, but also bulky parts with a high productivity.
This is what happens when you put the beam profiler under it. We get in mode 0 a more traditional Gaussian spot, and as we go through modes 1 through 6, we get this really interesting ring that's hotter on the outside and a nice cool spot in the middle. And that's going to really help us avoid that whole keyhole process. Now, a smart person probably would have done a DOE, stepping from mode 0 through mode 6. I'm kind of crazy, so I went straight to mode 6 because I wanted to compare. I know how bad my life is in a Gaussian spot. I wanted to know what this ring can do for me because it's 300 microns and it's hot on the outside and cold in the middle.
On the bottom, you see the different intensity indexes of the AFX laser in our simulations, which correspond pretty well to what we actually can measure in the system. And now that you have this, we can implement this in our melt pool dimension model, and look, we can get these kind of pictures. So you see the different melt pool index and the resulting melt pool dimensions as a top view. What we see is a reduction in melt pool length and an increase in melt pool width, and they also get a little bit less deep, so a little bit shallower. And this reduction in melt pool length is quite significant because that means that we get a more stable melt pool. Because if your melt pool gets very elongated, at a certain point you will achieve balling, where you don't longer have a very continuous track but different beats. Now that we have these melt pool dimensions, we can try to predict the process window in our system. To do so, we have to put some boundary conditions on what is a good melt pool dimension. So we want sufficient depth so that you can fully melt a single layer of powder. We don't want keyhole melting, so we put a limit to how deep the melt pool can be corresponding to its width. And we also want the stable melt pool, so we must limit the length of the melt pool can have relative to its width. And then we can get these kind of process windows. I'll start on the left with the one for the standard Gaussian index. The red process window is for 30 micron layer thickness, green is for 60, and blue is for a 90 micron layer thickness. And this is quite normal, what you're used to see. So it's limited by minimal depth, maximal keyhole, and stability criterion. What's interesting is now, if we do the same for the different intensity profiles, for example, here on the right, you see the full ring mode, we see a significantly increased process window. Why is this? Well, for one, as I said, the melt pool is shorter, which means we can push up this boundary limit of where it becomes unstable, which allows us to use higher production speeds, scanning speeds. And because we have a wider melt pool, we also can increase the hedge spacing. And what's actually counterintuitive is that we also have an increased process window for the deeper layers. You would say it's a shallower melt pool, sure, that's quite counterintuitive, but you have to think in it the other way around. Because we decreased the depth, we can put more power in the system before we reach the keyhole mode melting and the corresponding keyhole pores. So we can increase both the depth, the hedge spacing, and the speed, clearly showing the potential productivity increases. In our simulated process window, we see increases of more than 3 times the productivity without any defocusing, without any special system, just switching the laser intensity profile.
Here's another example. We did some simulation work between different beam profile. For example, left side you have an ideal Gaussian beam. In the middle is have like a donut shape. You can change the inside and outside ring diameter from our simulation code. You can see there's a small donut and a bit bigger, fatter donut here. And you can see from the Gaussian beam simulation between the other two, and you can see the penetration depths definitely it's become more shallower when you get a fatter donut motions because you spread the energy beam in a wider way in a spatial distribution. And if you see the top section for the melt pool and the melt tracks, you can see inside of the melt pool it's more stabilized. So it's a less dynamic motion from the melt pool when you go to donut mode or you go consider kind of a ring mode. So that give a lot of benefit is because to get a more robust process and release less spatter, you need a more stable melt pool during the printing. So from a simulation, you can study different beam profile, different diameter for donut mode, and we see a lot of benefit when you go to a donut-shaped beam profile than traditional Gaussian beam.
And here on this slide, you can also see the heat flux distribution together with the velocity vectors, both for these two extreme cases, so Gaussian and AFX1 index 6, which has most of the power in the outer ring. And here, what is used as the coloring variable is the evaporation pressure, which actually drives most of these velocity vectors. So because of having the centralized heat flux inside of the beam center, this gives a lot of velocity due to the recoil pressure, which is avoided in the index 6, and actually translates to a more stable melt pool with lower maximum velocities. And these maximum velocities, they can be responsible for spattering the process and actually ejecting the material outside of the melt pool.
What you can see here is a typical process window where you have a look on the laser power on the y-axis compared to the scan speed on the x-axis. And on the left-hand side, it's for a typical Gaussian beam profile for stainless steel material. The green areas are the areas where you have a successful processing, which means you have the right, density, for example, or the right combination of your welding width with your welding depth. If we have a look now on the other beam profile, so beam profile index 4, 5, and 6, what you can actually see is that you can increase the production speed, so the scan speed, and you get even for these higher laser powers combined with the scan speed, a stable processing window.
On the top right, you can see a typical Gaussian beam profile, and then a ring-shaped beam profile with the same diameter. On the table with the edged cross-section of a single weld track, you can see for different laser powers and scan speeds a comparison of the melt pool. For the Gaussian profile on the left, you can see some defects like protrusion or cracking, while for the donut profile this was not visible for the wide range of combination of process parameters we used. Also for the donut profile, the melt pool gets wider but not so deep. So, and this is quite interesting if we are thinking about productivity, because we don't want to melt like several layers of powder again and again, but we want to have a wide melt pool so we have less hatches.
By the way, you would think that the cube on the left has great microstructure and the cube on the right probably's got a bunch of porosity in it. Actually, no. They all look fantastic because this gentle ring, this hot on the outside, cold in the middle, nice gentle ring that takes away that Gaussian spot, that takes away that deep keyhole effect, gives us a much broader processing range from our materials.
Then we tried, okay, from single tracks, it's nice finding, but what is if we produce three-dimensional cubic specimens? In this case, it was an aluminum silicon scandium alloy. You can see the relative density we measured, colored here in green, almost 100% density, and red 99% density. If you look at the top right graph, it's red. So for this particular hatch distance of 200 micrometers with a Gaussian beam profile, we were not able to reach a final part density of better than 99%. While for the donut beam profile, very spectacular, we get regimes with almost 100% density, and this is a very big difference between the two beam profiles.
Now it becomes more interesting if we go back to this slide where I varied the different intensity profiles, and if we plot this on the index on the simulated process windows, we see for the index 1 that my parts that in reality led to dense parts falls nicely within the process window up top. But the one at the bottom, where we use the ring mode, the parameters here at the very edge do correspond nicely to the parameters that are no longer yield dense parts. So this is again an indication that we are looking in the right direction with our process window simulations.
And what you can see here is a slightly different diagram. Here we are in the area for the typical Gaussian beam profile. And if you compare these other results with the other beam profiles, you see that there are areas where you have less spatter formation. And what is important for us, of course, the cross-section of the melt is increasing. That's the result I've shown before. And we have this the formation of spatter. But actually the volume we create as spatter is lower compared to the typical Gaussian beam profile. And actually that's a quite good result. We have a huger melt pool, but actually the ejector volume is, from our point of view, for a specific combination of a beam profile, scan speed and hedge distance, and laser power decreasing.
So another observation we made is if we're looking at the process, at the byproducts, on the left side you can see the Gaussian profile and the byproducts and the sputter. On the right side from the donut profile, we reduce the number of byproducts per molten volume.
But now this spatter formation would just land anywhere and we wouldn't be able to find it because it just would go into solution and build a new alloy. So we added tungsten particles. Why tungsten? Tungsten has an extremely high melting temperature, so with the parameters we use for Ti64 and the base alloy, we will not melt it completely, so it won't get into any kind of alloy. And when it lands on the surface, even on another part, we will be able by cross-section just to count the amount of spatter particles we find there. Here we really see a strong difference. When you see on the Gaussian area, we have particles everywhere over the place. And in comparison, when we look at the ring-shaped beam profile, we see that this dropped to nearly 21% of this. So we have an extreme reduction of our spatter formation, which was already shown with high-speed imaging on the process zone itself, but we never saw it on the build plate or the part itself, which we see now here. We really have a mean reduction of our tracer particles by 75%. When we're using the ring point shaped profile. So we have a significant reduction of feedstock contamination due to beam shaping.
We can actually collect the soot, we can measure the soot particles count during the printing in real time. From our study, we see almost reduced by 50% of the soot reduction, with way higher power. So our speed, we can show about 2.5x faster than single mode. We go to insert number 6, and the soot is about 2.2x less. I think it's about 40% of the original level.
In the meantime, we double-checked our results because, okay, this was just on the surface and maybe we were missing some parts. But there again, tungsten particles prove very valuable as tracer particles because they are extremely dense and therefore we are able to detect them via a micro-CT scan. And here we see the same results. On the left side, we have an extreme amount of distributed particles over the complete area where we used our Gaussian beam. It's also not on the surface, but also in the volume. And when we look at the right side, there we nearly have no particles at all in the complete surface. And the only mass of particles is the area where the coater shoves them to this area and where the laser just sintered them together. But this is even more than 75%. This goes more to 95%, but we didn't do this comparison in all the specimens, so we stick with the 75% in the mean, but you see it's also even more.
Here's a picture during our study, just shown before. This is actual printing using index number 6 at full power, I think close to 1100 volt with high speed. And you can see, usually you can see some spatter coming out, but from our testing, we see much less spatter showing up during the actual printing process, which is a very good sign.
So we run the study with the ring and the Gaussian again and changed a little bit the setup. So we have a wider area of view. We see on the top view the Gaussian beam and on the bottom view the same process just with the ring beam. And the benefit is here we see much less spatters for that ring even in this qualitative view. And if we increase the frame rate, it's getting more clear that we have completely different formation of spatter, which can be very easily observed with the thermography.
For LC10MG or aluminum alloys that worked, what about a steel alloy? So we used our lab system and looked about steel and found similar results. So more impressive even, if you see in the middle graph, we could increase the productivity by 240%. And for this particular part in the top right, cost estimation about minus 46%.
We put in a realistic evaluation scenario. So we have 9 blades on our mid-size system with a part volume of 58 cubic centimeters. We compared 3 different parameter sets, our standard Gaussian one, and then 2 different parameter sets we have investigated with the AFX ring mode, but also used the Gaussian mode for the contours. So we have the same surface quality, nearly same part quality. For the calculation we have used normal constants of a machine preparation of an hour and half an hour for the part extraction, 100 minutes for inertization and the shielding gas cost. And to put that in a diagram, we see here that our standard process is around 70-hour printing time, and with the fastest parameter set we can go down below 20-hour printing time, which is a time reduction of 80%. And even if we use just the AFX50 parameter set, which is better in mechanical properties than the standard one, it's definitely up to 50% faster. And if we put that in numbers, it would be around 70% faster than with our previous parameter set.
With the nLIGHT laser, after a whole process developments, we found out, compared to the data sheets of machine OEMs, we could increase the build rate nearly 3 times. Maybe double the time if you use other numbers, while maintaining or even outperforming the quality in terms of density, which is shown here.
And then we thought of the case of printing turbine blades, since here the crystal growth parallel to the build direction or load direction is beneficial for the use case. We printed it with the defocused Gaussian one on the bottom, the index 3 in the middle, and index 6 on the top. And what you can see here on the right side of the EBSD images is that we were able to reproduce those results in a complex geometry. So we have the weak texture for the area of index 0 defocused and the sharp texture for index 6 with highly elongated grains along the build direction.
Short summary of the material we are targeting: high-speed steel, very good hardness, especially at elevated temperatures up to 600 degrees C. But in terms of LPBF processing, a nightmare. High carbon content is usually classified as non-weldable, so very challenging to process via powder bed fusion. So when you look at cut sections from these steels or even entire parts, depending on the process parameters, the geometry, you can end up with one of 2 things. Either you have a lot of hot cracks that form during solidification, or you end up with large cold cracks when you cool down the parts after the build and then have cracking of the entire part. In some cases, as you see, several millimeters of deformation just due to cracking. And these result from the complex temperature fields we have in powder bed fusion.
We had been printing or trying to print a part at Amaero for a customer. It was an H13 tool steel. Most people think that is an unprintable material because it's very crack prone. And it's crack prone because it does not like extreme thermal gradients. But think about printing. We take warm powder, convert it to boiling metal, and then back to consolidated hot metal in like 1 second. That's a very extreme thermal gradient. So we generated a lot of condensates, and we created horrible productivity. We're scanning at like 600 millimeters a second, which is half of a normal scan speed. You do that, and you can create really nice looking H13 microstructure. But as we're printing this part, and it was a very large surface area in this machine, it was almost over half of this build plate, 250 by 500 millimeters. And about 15 millimeters into it, we realized that just the volume of vapor we generated was going to overwhelm our filter. That about 20% into this build, we were going to clog the filter and we were done. So we never got to print the part, but it drove us to, what about this ring mode laser? What can that do for us? So on the far left, that's the traditional melt pool that we're used to seeing, these very deep bells. And in the middle here, this is the H13 in the XZ and the XY view. And what you see are these very, very shallow melt pools. They're not at all the deep pool that we're used to. There's no keyholing that's happening. And it's a nice wide, shallow pool, which means we can widen the hatch spacing. It allowed us to reduce the total laser power because we weren't wasting all this Gaussian power in the middle. So we reduced the laser power, widened our hatch spacing, reduced the condensate generation, lowered the volumetric energy density, and we took, this was impressive. So H13 is very unproductive, 7.8 cc's per hour. We got it up under these conditions to 9.7. That's a 24% increase. But I was just so amazed at how well this worked that I had to see how far I could take it. So I've never seen anyone print H13 thicker than 30 micron layers, so I decided, well, we'll go to 50. What can happen, right? So we did a whole series of DOEs, going faster, pouring more power in, scanning thicker, scanning faster. So I've never seen anyone who could print H13 at high scan speeds because it wants to crack. So at 50 micron layers, 800 watts, 160 micron hatch spacing, mode 6 ring, scanning at nearly 1600 cc's per second, we were depositing at 45 cc's an hour. That was 7 times more than we were depositing before. And that's almost twice what we consider a productive amount of deposition, even in a friendly alloy.
So there you can see that for all the different layer thicknesses, preheating temperatures, and also energy densities, you will in some way end up with cracks. You can have more cracks or less, depends. At room temperature it's mostly cold cracks, and then when you go up in temperature it's mostly hot cracking, but you are hardly able to produce crack-free or technically crack-free specimens. The amount of cracking really heavily depends on the geometry of our melt pool. So you end up with rather next to no cracks when you have a very shallow and wide melt pool, and you will end up with a lot of hot cracks, especially over several layers when you have some very deep and narrow melt pools that commonly occur in what we call transition mode welding. So which is quite common for standard LPBF processing parameters. So we figured out it would be very useful to do some additional tests based on the results we already had from the AFX. So we already knew that we can generate very nice and flat melt pools with it, even compared to the defocused Gaussian beam, similar diameter. You end up with a much wider melt pool, similar depth, which gives us enough leeway to have robust processing and do not end up with a lot of defects due to lack of fusion. I've brought a video of the process with the AFX laser. It works well. It's a really nice process. First impression is the process works fine. We will do in-detail analysis, melt pool geometry versus crack formation, and we really see a lot of potential when it comes to processing of these hard-to-weld materials that are very sensible when it comes to the temperature fields and the continuous remelting. And the potential for AFX is obviously that we have additional degrees of freedom apart from preheating to very high temperatures or modifying just our laser power scan speed and hatch distance accordingly. We also have the control of our intensity distribution, which then helps us to control the solidification conditions and therefore reduce cracking in these components.
Which brings me nicely to our prospects and conclusions. We predict productivity increases of up to 3 times without any special defocusing. And actually, I will give you a sneak peek at how this can be implemented in reality. Up top, you see an impeller design that's processed in the standard way, Gaussian mode. And the bottom, you can see the same design, but now in a multi-index processing where the contour is scanned with your standard Gaussian, the same parameters as the one at top, and you see similar surface quality. But filling is done with the donut laser. And what we see is a doubling of the theoretical productivity. And this is not even the most optimal parameter set for productivity. This was just a set that we know yields dense parts. And I can already see a doubling of productivity. And if you look at the amount of energy we put into a single volume of metal, we actually increased or decreased the energy required to melt material by 20%. So without even trying, we doubled the productivity and reduced or increased the energy efficiency.
So, what are the benefits that we've observed? We can use the full 1,000 watts of this laser, and I could probably actually use 2,000 watts. I've deposited in layer thicknesses as high as 150 microns. I think I could get to 300 if my friend's gas flow and filtration will be cooperative with me. We demonstrated greater than 100 cc's an hour. We probably could get to 200 cc's an hour with good gas flow. And again, the gas flow is the problem. Half the condensate, but we're depositing 5 to 10 times the amount of material per unit time, so we're filling the chamber with condensate. Great tool, amazing laser. Here's some parts that were made on the EOS M290 with this laser. There's also an economy machine out there. The folks at Open Additive sell their system with this laser in here. Does phenomenal work.
For summary, with the remote laser, we think it's a very great tool to help us change the beam energy profile distribution, which help you improve the efficiency for energy coupled into your material. In the same time, you also keep the benefit of the depth of focus and also the spot size you can leverage between different modes. You can change that. So one more benefit we found is, since we are also building laser printing machine, so we like to get a simple integration laser solid. So I think this laser, after our testing, can be easy to plug in to test. So there's a less integration work we need to do, which is a good thing for us to take and test that. So for summary, we demonstrate about 2 to 3x productivity gain, and with about 50% of soot reduction using the index number 6 mode for the testing. But in the future, like I said, we like to test how we can print a part with the mixed mode together. For some portion, you have like an index a single mode. For some other portion, you have index number 6, like which is ring mode, or some of them you have something in between. I think to do specific location-dependent mode printing, that will give us a lot of benefit in the future, not only for speed, also for the quality. Thank you for your attention.
Thank you.
Thank you.
Thank you very much for your attention.
Thank you very much for your attention.
Thank you very much for your attention.
Thank you for your attention.
Thanks for having me.
Thank you. There's my email address, plus the folks at nLIGHT are welcome to give you my contact information if anyone has any questions, and I'll be around all week.
Thank you for your attention.